Let's see how we can calculate the frequency of alleles. We have this equation from Hardy-Weinberg. Well, P plus Q equals 1, and P is the frequency of the dominant allele, Q is the frequency of the recessive allele, and if you add how many dominant alleles and how many recessive alleles are in the population, you end up with 1, so all the alleles of the population equal 100%. And the other equation is about the genotypes, genotype frequency. So these are actual organisms. Keep in mind that each organism has two alleles. If that organism has two dominant alleles, that's a homozygous dominant organism, and the chances of being a homozygous dominant organism in that population depends on the proportion of the dominant allele. So it's the chances of having two dominant alleles that is given by the term P squared. I encourage you to review the rules of probability so that you know when you're adding and multiplying probabilities. The frequency of heterozygous is given by the term 2pq, which is the chances of having one dominant allele or one recessive allele, plus the chances of having a recessive allele and a dominant allele. Since there are two ways in which you can be heterozygous, you can get a dominant allele from your mother or from your father, and a recessive allele from either your mother or your father. And the frequency of the homozygous recessive is given by the term q to the square. This is the proportion of the recessive alleles in the population to the square. When we're looking at these two equations, the top equation is looking at the actual alleles in the population, while the second equation is talking about organisms in that population, what genotype those organisms will have. So let's look at this population of black and white cats. And we know that black fur is dominant to white fur. So if you look at these cats, which of these ones do we know for sure their genotype? We don't know if a black cat is a homozygous dominant or heterozygous, but we know that the white cats are homozygous recessive. And out of the 25 cats that we have here, 4 out of 25, which is 16%, are white cats. And this is asking us, what is the frequency of the B allele? So what is the frequency of the recessive allele? Which term is this asking us for? Keep in mind that the first equation estimates the allele frequencies, while the second equation estimates the genotype frequency. So what term is this question asking for? And this is asking us for Q. The frequency of the recessive allele is the term Q. What is the term that we know from this problem? And it's given us the term 16%. It's saying 16% of the cats are white. So we know that 16% of the cats are homozygous recessive. What term does 16% correspond to? The term that we know is Q to the square, because Q to the square is the frequency of the homozygous recessive individuals in that population. So we know that 16% of the cats are homozygous recessive, which means 16% equals Q to the square. From there, we use this equation to calculate Q. So since we know that Q to the square is 16%, or if you denote it in frequency, it's 0.16, now we can get the square root of 0.16 to get Q, and Q equals 0.4. Now this question is asking, what is the frequency of the dominant allele, which is the term P? Since we know Q, we can calculate P because P equals 1 minus Q. Q is 0.4, then P has to be 0.6. On the other hand, if we knew the genotype of each of these individuals in the population, if we were able to see which cats are heterozygous and which cats are homozygous dominant, this cat is actually heterozygous, but this one next to it is homozygous dominant. Although phenotypically they look the same as the homozygous dominant, if we could see what are the actual genotypes of each one of these cats, we could count the alleles individually. We take the alleles from our population of cats and we group them by those that are homozygous dominant, that have two dominant alleles, those that are heterozygous, that have one dominant and one recessive allele, and those that are homozygous recessive, that have two recessive alleles. And we count how many alleles in total do we have. So since we have 25 cats and each cat has two alleles, we have a total of 50 alleles in our population. Let's look at how many of those alleles are dominant. So of the 50 alleles that we have in our population, note that we have twice as many alleles as cats because each cat has two alleles. The 9 homozygous dominant cats each contribute 2 dominant alleles, so we have a total of 18 alleles. There are 12 heterozygous cats. They each only contribute 1 dominant allele because the other allele is recessive. So these cats only contribute 12 dominant alleles to the population. And the homozygous recessive don't have any dominant alleles, so they contribute 0 alleles to the population. So the total dominant alleles in our population are 18 that come from the homozygous dominant and 12 from the heterozygous. So that's a total of 30. And we have 50 alleles in total, so 30 over 50 equals 0.6. The frequency of the dominant allele is 0.6. So 60% of the alleles that we have here, of all those 50 alleles that we have here, 60% of them are dominant. Now that we know that 60% of the alleles present in this population are dominant, we know the remaining 40% are going to be recessive alleles. So we know that Q is going to be 1 minus 0.6, which is 0.4. Q is 0.4, so 40% of the alleles in the population are recessive. Let's look at this other example using Japanese 4 o'clock flowers. These flowers have incomplete dominant. Flowers that are homozygous dominant have red color flowers. Flowers that are homozygous recessive have white color flowers, but heterozygous flowers have an in-between color. They're colored pink. This is telling us the frequency of the recessive allele is 0.2. What percentage of the population will be pink? What percentage of the population will be heterozygous? So what term in these equations is this asking us for? This is asking for the term 2pq. This is the percentage of heterozygous in the population. And it's given us that the frequency of the recessive allele is 0.2. So what term is it giving us? And the term that is giving us is Q. So it's giving us the percentage, the frequency of the recessive allele in the population. So if we count all the alleles of all the flowers in this population, remember each flower contributes 2 alleles, the proportion of these alleles that are white will be 0.2%. Now that we have Q, we can obtain P using this equation. So we know Q is 0.2 because this is given in the question. P will be 1 minus Q, so P will be 0.8. And we can use that now to calculate, using this equation, calculate the percentage of heterozygous in the population, which is the term 2pq. So now that we have P and Q, we calculate 2pq, which is 2 times P, which is 0.8, times Q, that is 0.2. And that gives us that 2pq is 0.32. So 32% of the organisms in this population will have pink flowers, which are heterozygous. So keep in mind the difference when we're looking at the percentage of alleles. We're looking at the alleles that are present in the entire population versus when we're looking at the genotypes that organisms will have in the population. So each individual contributes 2 alleles to the population. If they're homozygous dominant, they contribute 2 dominant alleles. If they're homozygous recessive, each individual contributes 2 recessive alleles. And if they're heterozygous, they contribute 1 dominant allele and 1 recessive allele to the population. And Hardy-Weinberg assumes that all individuals in the population have equal chances of mating. So we take all the dominant alleles in the population and all the recessive alleles and we put them in a big bucket. And this is what we refer to when we say a gene pool. We're talking about all the alleles present in the population. So we're not talking about the actual individuals or organisms. We're talking about a number of alleles that are present in that gene pool. And we're assuming that any individual can have equal chances of mating with any other individual in the population. 80% of the eggs produced in this population will have the dominant allele, and 20% of the eggs produced in the population will have the recessive allele, while 80% of the sperm produced in this population will have the dominant allele, and 20% will have the recessive allele. So the percentage of the alleles determines what percentage of the gametes will have the dominant allele, 80% will have the recessive allele. And then we can look at what will be the result of those gametes in the next generation. So this looks similar to a Punnett square, but it's not a Punnett square because here we're not looking at a specific mating. We're looking at the entire next generation for that population, all the individuals born in that population for the next generation. Since 80% of the sperm produced and 80% of the eggs produced have the dominant allele, 64% of the individuals in the next generation will be homozygous dominant. While the chances of combining a dominant allele with a recessive allele or a recessive allele and a dominant allele here will give us a heterozygous. 16 plus 16%, 32% of the individuals in the next generation will be heterozygous, and combining a recessive sperm with a recessive egg will give us the homozygous recessive individuals. 0.04%, which is Q squared, are the homozygous recessive individuals in the population. So this is another way to look at how this equation is coming from, using the proportion of the alleles to calculate the genotypic frequencies. The proportion of homozygous dominant individuals in the population will be the chances of two gametes with dominant alleles finding each other, which is given by p to the square. And the chances of a heterozygous is one recessive allele with one dominant allele, or one dominant allele with a recessive allele here, which are QP or PQ in here, and those two add together, so this is 2 times PQ, give us the percentage of heterozygous in the population. And the chances of two recessive gametes coming together is Q to the square, and that gives us the proportion of homozygous recessive in the population.